In this video, we're going to talk more about empirical and molecular formulas and show how to actually calculate them if we know some of the elemental composition information about a compound. So just as a refresher, let's review what empirical versus molecular formula means. Now, earlier we were talking about fructose. The molecular formula for fructose was C6H12O6. So that tells us exactly the number of carbon, hydrogen, and oxygen atoms that make up one molecule of fructose. If I was going to report the empirical formula, I would really be reporting just the ratio of those elements to one another in fructose. So I would divide everything by the lowest number of atoms or lowest number of moles of one of the atoms. So that would look like C6 divided by 6, 6 being the smallest number, H 12 divided by 6, and then oxygen 6 divided by 6, which would give us an empirical formula of CH2O. Really different, right? So we're going to first look at how to determine an empirical formula from mass, and then we're going to take a look at that process from percent composition. So if we know the mass of each type of element that we have in our molecule, then it's actually pretty easy to get to an empirical formula. What we need to do is take that mass that we have for each atom and divide by its molar mass to get to the number of moles of our individual elements that make up that molecule. And then once we have the number of moles for each of these elements, then we can actually, we have a mole ratio. But to get the empirical formula, we need to make sure that we're showing that mole ratio in the smallest possible numbers. So we're going to divide by the lowest number of moles, and that's going to give us this mole ratio that's kind of our least, or a minimized one. I don't quite have the right word for it. So once we have that, then we convert that ratio into our empirical formula by using that ratio as the subscripts after our elements in our formula. So really it's three steps. We get into our moles, we get into the lowest ratio of our moles, and then we build the formula from there. So if then at that point, once we have our empirical formula, if we know the molar mass of our compound, then we can actually go ahead and figure out what the molecular formula is. Because we can see how many times you have to multiply that empirical formula on itself to be able to reach that molar mass. So if I multiply my empirical formula's formula mass by 2, then my molecular formula would just be that empirical formula. Each of the subscripts would be multiplied by 2 to get to the molecular formula. So let's talk about an example of this. And I caught right before I did this typo in the lecture slides. So we're looking here not at percent composition yet. We're talking about the mass of elements. If we know that piece, then we can find the empirical formula. And that's what we're going to do in this example. So we have a compound that's made of 40 grams of carbon, 53 grams of oxygen, and 7 grams of hydrogen. And we need to determine what the empirical formula is. And so remember, we're going to take a problem-solving strategy here that is going to first convert into moles. 2, we're going to reduce the mole ratio. And 3, we're going to write our empirical formula. All right, so first, we have our first step right here, which is converting that mass into moles. So we're going to do this for each individual element. So we just need to pull the molecular weight from the periodic table for that element. So if I have 40 grams of carbon, I would use the molar mass from the periodic table for just carbon, which is 12.01 grams per mole. So setting this up so my units cancel out and I'm left with units of moles, I'll divide 40 by 12.01 and I'll get 3.3 moles of carbon. Now I'm going to go through that same process for hydrogen and then repeat that process for oxygen as well. And so my hydrogen, which I have 7 grams, I'll divide that by its molar mass of 1.008 and I'll get 6.9 moles of hydrogen. Now my 53 grams of oxygen will be divided by its molar mass of 15.99 grams, and that gives me 3.3 moles of oxygen. So I have 3.3 for carbon, 3.3 for oxygen, and 6.9 for hydrogen. My smallest number amongst these mole values is 3.3. So that means I'm going to divide everything by 3.3. When I divide 3.3 by 3.3, I get 1. When I do 6.9 divided by 3.3, I get 2.1. So now I have a simplified mole ratio. I've reduced it. It's as small as it gets. And I know that that 2.1, that decimal place, is concerning because we cannot have 0.1 of an element at all. But if we look at the mass that we have here, it's only 2 significant figures. And so that's going to, that's not like a very accurate assessment. We're going to have a range of values, right? So when I see 53 grams of oxygen is measured, I know it's somewhere between probably 50 and 55 or 50 and 60 for that measurement, which is a bit of a range. So we might get decimal places, and that is okay. What we're going to do is essentially treat our mole ratios like one significant figure, and we're going to round. And so this 2.1 is going to become a 2, and the 1 stays a 1. So my chemical formula is going to be carbon 1, H2, oxygen 1. And we always omit those ones in our mole ratios when writing our chemical formula. So that's going to simplify to CH2O. So now let's assume we do know the molar mass. We were able to get the mass of each element. We did an elemental analysis of a new compound possibly. And we were able to get the molar mass from it as well. And we have a molar mass of 90.075 grams per mole. Well, the first step to do is to take our empirical formula, this CH2O, and determine what is its formula mass for that empirical formula. And so since I have 1 carbon, I'm going to have 12.01 plus 2 hydrogen, so 2 times 1.08 plus 15.999, the molar mass of just an oxygen atom. And I get a formula mass of 30.025. I'm going to make a better box. So my empirical formula represents about 30 grams per mole. And I know my molar mass for my compound is about 90. So it sounds like I really have within my molecular formula 3 empirical formulas worth of elements. But let's confirm. So I'm going to take the molar mass for the compound and divide it by the empirical formula. And when I do that, I'll get a value of 3. So with that information, to determine what the molecular formula actually is, I am going to multiply each one of my coefficients by 3. And if there's nothing for a coefficient, like after carbon, that means there's really a 1. And so that becomes a 3. And the hydrogen is a 2, but multiplied by 3 becomes 6. And our oxygen, which was 1, becomes a 3. And so our molecular formula is this C3H6O3. Okay, but that's doing the problem from mass. Another kind of curveball that comes with this is it might be percent composition that you're looking at. So let's walk through how to handle a percent composition version of this same problem. So we have an example of carbon dioxide.